All right, welcome back. Today we're going to be building ourselves a drive shaft loop. We're going to go and do some reasons why you need one, why they're important. Just a quick disclaimer, every track sanctioning body has different rules. We're basing it off the NHRA rules. Their minimum tube diameter is 7/8 by 0.65 wall. This one is 1 inch by 0.125 wall. We're making it a little thicker just to be safe. And the weight disadvantage really isn't bad. I mean, this whole thing probably weighs 4 pounds. So let's get into making it. All right, everybody. Why is math important? Math might suck, but when you're building a race car, you want to leave out all the guesswork. Math essentially guarantees that everything you do is going to be exact or as close as possible without wasting material or screwing up a bunch like I like to do. Well, we know I have a 4-inch aluminum drive shaft, which means we're going to need at least a 5-inch inner diameter drive shaft loop to clear. That leaves us a 1/2 inch on either side. We also need it roughly 12 inches high. This will vary depending on your vehicle and drive shaft size and whatever. We're using 1-inch DOM tube drawn over mandrel. It is 125 wall or 1/8 inch. It's mild steel. So now that we know the rough dimensions we need, here's the equations to make it work. We have arc length, inside radius, and cut length. Arc length, pi times centerline radius. We're using a 3-inch centerline radius die on our JD2 Model 32 bender. So for 3-inch, you would do pi times 3. That equates to 9.42 inches. 9.42 inches is the material consumed by the die in the bend. So for example, we take this piece here. I have the CLR scribed out on the tube. I have the start of bend and the end of bend. Now if I did everything correctly, it should equate to roughly 9.5 inches. There we go. That looks like 9.5 to me. So this is why math is important. You can use it to eliminate all the guesswork and know that your finished product's going to come out correct and that you haven't wasted any material. The next step is inside radius. That is your outer diameter divided by 2, and you subtract that from your centerline radius. We have a 1-inch tube, so you divide that by 2, that equals 0.5. So then you'll take your CLR, 3 minus 0.5 equals 2.5 inches. That is your inside radius. Now you'll take 2.5 inches times 2, and that equates to 5, and that is a 5-inch diameter. That was our goal. We will have a 1/2 inch of clearance on either side of the drive shaft. Your cut length is both legs added up plus your bend radius. So we have two 12-inch legs on either side plus 9.42 inches in the 180-degree bend. That equates to 33.5 inches. I recommend cutting it long just in case, but this gives you an idea of how much material you'll need and removes the guesswork. All right, everybody. I figured I'd throw in a little quick tip here. This is for if you have a JD2 Model 32 bender, and if you've struggled with finding the start of bend on your tubing, I'll show you a quick and easy way to figure it out. So here's a 3-inch centerline radius die for 1-inch tubing, and in order to find the exact start of bend, all we're going to do, take a caliper, measure the hole, and it comes out to 1 inch. So you split it in half, 0.5, and find the edge of your circle, left edge towards where the pipe clamp is. And to make it easier for marking purposes, you can take a straight edge, center of your pivot right here, down to your first hole, scribe a line down, and then go from that line over 1/2 inch. And then what I did is I just took a cutoff wheel and took a little bit of material out, not enough to get into the actual die face, and put a red mark in there. Now every time you want to line up a bend, this is where the start will be. Alright, so now that we've went over the start of bend, we're going to mark our desired height. Our height is going to be from the edge of the tube to the start of the bend. Of course, there's going to be another roughly inch where the bend is, but this gets us started. So I'm going to mark 12 inches. All right. And now, simply all you have to do is take this little mark and line it up with the mark on your die. And that's exactly where the start of your 180-degree bend is going to be. If you chose to use ERW tube, make sure that the weld seam is facing you and not up or down on the bend. Now, we're going to put some pressure on the tube. Alright, now that the tube's in there solid, we're going to set our 0. And bend to 180. By the way, I did not check what the spring back of this tube was going to be. So we're just going to keep bending it until we get the desired angle. Okay, and there we have it. That's the start of a drive shaft loop. So why was all this boring math important? Basically, it proved on paper that this was going to fit our drive shaft no matter what. Looks like it fits to me. 4-inch PST drive shaft and a 5-inch inner diameter drive shaft loop. We'll have plenty of clearance. The rules state within 6 inches of the front U-joint, we'll still have plenty of room. Now we need to make the cross member this is going to get welded to. So the next step in the process is to build a cross member for the drive shaft loop. There's 2 main reasons why we're building this as a standalone device and not connecting the loop to the transmission cross member. First, for a rule-abiding drive shaft loop, it has to be fully enclosed. It can't just be this hanging out in the air with some standoffs. And then you have to think about the load path too. So if I were to weld this to my transmission cross member and the drive shaft decides to exit the chat, it's going to take the transmission out with it. When the drive shaft breaks apart and rattles around in here, it's probably going to tear the cross member. It's probably going to break the tail shaft housing and cost a whole lot more money. So if you build this cross member by itself, standalone, and tie it into the frame, all the shock load from a drive shaft exploding is going to be transferred through this and into the frame. So to start the cross member, you want to know the width of your frame. This one I already pre-cut. It's 45 inches edge to edge. That's exactly 45 inches, which means it's probably not going to fit, and we're going to have to cut it down, but we're in the mock-up stages, so that's okay. So when you've got your cross member length figured out, you're going to need a way to mount it to the frame. You can make your own mounts. Find something in your metal pile that's going to work out perfect. Or, I don't know. Anyway, the basic gist is I'm going to take these little 90s or L brackets, and I'm just going to weld the tube right to the face of them. And then we're going to take 4 3/8 grade 8 bolts, and that's how we're going to mount it. So now we need to cut, measure, and weld. Alright, please make sure to check your local track's rules, regulations, and your sanctioning body's rules and regulations, and don't take my word for it, because I make mistakes. But we'll see if it passes when we get there. Alright, so now that we've got our brackets mounted up for our drive shaft loop cross member, I'm doing a final measurement to cut it to length. I originally started off at 45, which is the frame width outside to outside, but with these L brackets, it is at 40.5. So we're going to cut this tube, test fit it, and go from there. Now don't forget, drive shaft loops are there so your butt doesn't get an extra hole. They do make Scotch-Brite belts for belt sanders and grinder attachments. That way you can prep this whole tube at once prior to any fabricating or bending, and it makes life a ton easier. I just haven't bought one yet. Alright, so instead of eyeballing like earlier, we're going to find the angle. We're actually not going to find any angle. We're going to zero the angle of the drill arbor, and then we're going to go up to our workpiece. Look at that, 0.1. Oh, that's good enough for me. 0.1, 0.0 should be fine. All right. We're cutting it the right way this time. We're cutting it level. We're cutting it on our line so it's even and level on the cross member. All right. So obviously we're going to trim up these copes just a little bit, but the major chunk of material is gone. Fit up looks perfect. So after you coat these joints with the hole saw, you can see how rough and sharp they are. We're going to go through now with a flap disc, and you can see on the edges they're paper thin, and you can't weld this to your main cross member. Well, you can, but it's not going to be strong. You essentially want to flatten these out a touch so that the actual tube thickness is the same all the way around. So that way, when you're welding it, you have the same amount of material welded to the same amount of material, and you don't have any thin spots on these edges. Just the same way you would do a roll cage. Okay. There you have it. Alright, so now that you've went through and smoothed out all your joints, the material thickness should look very even all the way around. And you'll notice when you fit it up to your tube, you actually have material that you can fill weld into. There still shouldn't be any gaps, but you should have the material thickness of your pipe all the way around. So of course we're going to TIG weld these like everything else. Clean up your areas to be welded with acetone afterwards, including the insides of your pipe, or else you're probably going to have a bad day. I better not hear any comments about how I'm cleaning this freaking tube. Alright guys, so when you've got your tubes all mocked up and set, you're ready to clean it up one more time and tack. If you're clever, you've probably noticed that I've shortened my drive shaft loop considerably. It was way up there. But if the drive shaft were to break, you really want to give it the least amount of room to start flying all over the place. So I've trimmed it down another 3 inches. It's got maybe 3/4 of an inch of room up top and 1/2 inch on either side. The drive shaft is at full extension right now, but on full compression, it still doesn't come close to the top. So now we're going to tack her in and finish welding it. These fuel lines have been blown out, by the way. Alright, that should be good enough to take it out and finish welding it. Alright, so we got it all welded up. It looks finished, but I'm going to add some gussets. This is a safety item. It's going to keep the drive shaft away from you, away from people, and off the track. So the stronger the better. The only reason for this is to contain the drive shaft. I'm not using it to stiffen the chassis, nothing. It's just to protect the driver. So we're going to add 45-degree gussets on each side of the drive shaft loop, or one. And then we're going to take, come on now. And then we're going to take some 1/8-inch plate steel, and we're going to weld it on the back side like that. And then we're going to call it good. I did also radius each corner of the triangle, because if you just go to a straight edge, it promotes cracking. So try to round off everything. Plus it looks a little better. And we'll catch back up with you when I'm done. And pick up all my before. Alright guys, this is the finished product. All gusseted, fully welded. Now the moment of truth, we're going to see if it still fits. Alright, I'm not going to tighten it up because we're just going to pull it right back off and paint it. But that's the idea. I'll shove the drive shaft barely in. Alright, there we have it. That is the finished product. Now if you notice, there is a little bit of lean back on the actual hoop itself. I think roughly 15 degrees. I did that because it sort of forces the drive shaft down. If it decides to come loose, when it goes up, it'll kind of push it down. And because it more or less encompasses more of the drive shaft. If you had it straight up and down, it's only going to protect just this 1-inch area. Whereas if you have it at a slight angle, it covers 2.5, 3 inches more. Alright guys, that's a wrap on the drive shaft loop video. Please let me know down in the comments what you'd like to see next, and thanks for watching.